In this video, we will animate contraction mappings in order to visualize value function iteration and convergence. For many of us, visualization is a powerful tool for understanding mathematical concepts. For example, suppose you had never seen a circle. You could be shown this equation and be told this is the equation for a circle in two-dimensional Euclidean space, with its center at the origin and with a radius of 1. You could also be shown this picture, which is a graph of the equation. Many of us would find that this picture gives us a deeper and more confident understanding of the concept of a circle than the equation by itself. In many disciplines, we encounter the concept of value function iteration. We start with a Bellman equation that provides us with a Bellman operator. Under certain conditions, the Bellman operator is a contraction mapping. Repeated application of the Bellman operator then converges to a unique fixed point that is the value function. Let's develop an example from economics that we will use later in this video to visualize the process of value function iteration and convergence. This example is a simple version of an optimal growth model. Imagine that you are Robinson Crusoe marooned on a desert island. Potatoes grow on the island, and each season you need to manage how much to eat and how much to plant for the next season. The problem is how to eat and cultivate potatoes optimally. More formally, each season is a discrete time period indexed by T. You start with some available resources of potatoes denoted by A greater than 0. You consume C between 0 and A to get utility U of C, where U is a utility function. You plant K equals A minus C potatoes, the potatoes you do not consume, to get a new harvest F of K next period, where F is a production function. We suppose that you live forever, and your goal is to maximize your lifetime utility, which is given by this discounted sum. You maximize this discounted sum subject to these feasibility constraints and subject to the amount of the resource with which you started. Define V of A as the maximum lifetime utility if your initial resource endowment is A. We expect it to be increasing in the amount of the resource with which you start. Using this definition, we obtain the Bellman equation, which says that we achieve maximum lifetime utility by choosing current consumption to maximize the sum of current utility and discounted maximum lifetime utility next period. Note that maximum lifetime utility next period depends on the amount of resource with which you start next period, which in turn is given by F of K equals F of A minus C. We call V of A the value function. We define the right-hand side of the Bellman equation as the Bellman operator T. We can then write the Bellman equation compactly as shown. We see that application of the Bellman operator T to V outputs V. That is, V is a fixed point of T. If T is a contraction mapping, repeated application of T starting from an arbitrary V0 must converge to V. That is, Vn converges to V as the number of iterations n tends to infinity. The goal of this video is to visualize this process of value function iteration. Here is the plan for the remaining 20 minutes of this video. The fixed point to which value function iteration converges is a function, but we will start by visualizing a contraction to a fixed point on the non-negative real line, which is easier. We will use this to visualize the importance of the modulus of the contraction mapping, which in the example from the previous two slides was beta, the discount factor. Then we will return to value function iteration, but begin with a special example where we can solve explicitly for the value function. We will use this example to visualize contraction to a closed form value function. That way, we can see in advance the function toward which the iteration is converging. We then return to the example of the previous two slides, which is typical in that we can only solve for the value function numerically using value function iteration. We will use this example to visualize numerical solution for a value function using a contraction mapping. A link to a paper that rigorously develops the mathematics behind this numerical solution is given in the description that you see in YouTube just below this video. In animations, we will show convergence to the value function from a conventional start and from an unconventional start. Let X be a point on the non-negative real line. T is an operator we apply to X that outputs alpha plus beta X. When T gives us back the X with which we started, that X is a fixed point of T. We call that fixed point X star. We can solve the equation X star equals T X star and see that T has a unique fixed point equal to alpha over 1 minus beta. We will see that T is a contraction mapping for beta greater than or equal to 0 and less than 1, meaning that repeated application of T starting from any initial value of X must converge to the fixed point X star. To visualize this iterative process, we must choose values for the parameters of T. Let's choose alpha equals 1 and beta equals 0.9. Plugging in, we compute that the fixed point of this operator is 10. We can check that 10 is the fixed point by applying the operator to 10. We get 1 plus 9 equals 10. Now let's apply the operator iteratively, starting from an initial value x0 equals 0. The first iteration gives us 1 plus 0.9 times 0 equals 1. For the second iteration, we apply the operator to 1, which means we have applied it to the initial value 0 twice. This gives us 1 plus 0.9 times 1 equals 1.9. We continue along these lines for the third iteration, which gives us x3 equals 2.71. The more iterations, the closer we get to the fixed point 10, and as we let n go to infinity, we must converge to this fixed point. Let's visualize this iterative process on the non-negative real line. We start from an initial value of 0 and then obtain x1, x2, and x3. Repeated application of the operator brings us as close as we want to the fixed point. Here is the entire iterative process from beginning to end. In our notation, beta is the modulus of the contraction mapping provided by the operator T. Now we will demonstrate visually why beta must be less than 1. This graph plots the jth iteration of X on the horizontal axis and the next iteration of X on the vertical axis. When the next iteration is the same as the jth iteration, we are on the 45-degree line. The blue line is the operator T applied to X, that is 1 plus 0.9 times X. It intersects the 45-degree line at 10, so 10 is the fixed point of T. Because 0.9 is less than 1, The slope of the blue line is less than the slope of the 45-degree line, and the blue line must intersect the 45-degree line from above. As a consequence, any xj less than the fixed point must yield a higher xj plus 1, so the xj's converge to the fixed point. We show the result of starting from x0 equals 0 in green. We obtain x1 equals 1, which we feed into the operator to get a still higher x2, which we feed into the operator to get a still higher x3, and so on. The next graph makes the same point more generally. The blue operator has a slope less than 1. Feeding an x0 that is less than the fixed point into this operator yields an x1 that is greater than x0, which in turn yields an x2 that is greater than x1, and so on. The orange operator has the same fixed point, but its slope is greater than 1. Feeding the same x0 into this operator yields an x1 that is less than x0, which in turn yields an x2 that is less than x1, and so on. If we pick an x0 that is greater than the fixed point, the blue operator again leads us toward the fixed point, and the orange operator leads us away from it. Thus, the blue operator is a contraction mapping and the orange operator is not. Consider the example, t applied to x equals -1 plus 1.1 times x. You can verify that it has the same fixed point, 10, as t applied to x equals 1 plus 0.9x, but that any x0 not equal to 10 will lead away from 10 instead of toward it. Now we are ready to move on to value function iteration. For ease of visualization, we consider value functions that can be plotted in two-dimensional Euclidean space. Moreover, to ensure that the conditions are met to guarantee that repeated application of the Bellman operator converges to a unique fixed point, we place an upper bound x bar on the argument of the value function. Now the contraction occurs in the space of continuous functions defined on 0x bar, and the fixed point is a function instead of a point. In terms of visualization, the contraction mapping will yield a series of curves that converge to a fixed curve instead of a series of points that converge to a fixed point. The fixed curve could look like this, or this, or this, but there are curves that are ruled out. This curve representing the function 1 over x is ruled out because it is not defined at 0. This curve is ruled out because the function is not continuous. This curve is ruled out because it is not a function. To repeat, the contraction mapping we will illustrate is a Bellman operator provided by a Bellman equation, and the fixed point of the Bellman operator is a value function. Rarely can we solve directly for the value function. Instead, we find it numerically by applying the Bellman operator iteratively. Deepen our understanding, however, we will first consider a problem where we can solve for the value function directly. That way, when we show the convergence animation, we will see where the convergence is heading, just like the convergence in the non-negative real line that we saw earlier. In this Bellman equation, V of ST is the maximum payoff over an infinite lifetime from your stock of work relationships at time t, where S is the stock of colleagues with whom you work well. You build your stock of work relationships, your network, by meeting with colleagues you don't know. If you find out you work well with them, you continue to meet with them in the future. The probability that you work well with an unknown colleague equals P. Hence, your stock of work relationships in T plus 1 equals your stock in T plus P times your meetings with unknowns M in T. In every period, you obtain benefit B from meeting with each colleague in your network, plus an expected benefit P times B from each meeting with an unknown. These meetings cost you effort and time, and your cost function, C, has a positive second derivative, increasing marginal cost of meetings due to congestion. In each period, you choose M to maximize the sum of your current and discounted future payoffs from meetings where beta is the discount factor. The right-hand side of the Bellman equation defines the Bellman operator T, where we have dropped the time subscript to save notation. Using the Bellman operator, we can rewrite the Bellman equation compactly as shown. We see that the value function V of S is a fixed point of the Bellman operator T. You apply T to V and you get back V. It can be shown that the solution to this Bellman equation, that is, the fixed point of the Bellman operator, is given by this line with a positive slope and positive intercept. Z bar is defined by this equation and can be interpreted as a target network size, where the current plus future benefit of meeting with unknowns is just equal to the marginal cost of additional meetings. V of S is increasing in S because the larger is your network, the less time you need to waste meeting with colleagues with whom you may not work well. V of 0 equals your maximum lifetime payoff if your initial network size were 0. In the paper, to which you can link in the YouTube description of this video, we verify this solution. That is, verify we have found a fixed point by simply substituting it back into the Bellman equation. Now we will visualize convergence to the value function we verified. We use value function iteration. To choose the upper bound on the argument of the value function, we note that the rule for optimal choice of meetings with unknowns, M star, is M star equals Z bar minus S. As your network size approaches the target, your desired matches with unknowns decrease. This rule implies that S greater than Z bar requires a negative number of meetings with unknowns. We therefore choose Z bar as the upper bound for S, and we consider functions on the interval 0, Z bar. It can be shown that for beta greater than or equal to 0 and less than 1, the Bellman operator for this problem is a contraction mapping with modulus beta on the space of continuous functions on 0, Z bar. Repeated application of this Bellman operator then guarantees convergence to the fixed point, just as did repeated application of the contraction on the non-negative real line. The first iteration applies the operator to an initial choice V0, making the standard choice V0 equals 0 yields a simple expression determining the optimal number of meetings, which in turn leads to a simple expression for V1. That simple expression is fed into the next iteration. The second iteration applies the operator to V1, and so on. To show the results of this iterative process numerically, we need to choose a functional form for the cost function and values for the parameters. Here is a cost function displaying increasing marginal cost and an odd parameter combination for eta, which is chosen to make Z bar come out to be a nice round number. Z bar is determined by this equation that we saw on the previous slide, which after substitution and simplification leads to Z bar equals 100. Here, the blue line is the value function after we have plugged in the values for the parameters. We see that it is a continuous function on the closed interval 0, 100. Starting from an initial guess, the Bellman operator will give us a series of such functions that will converge to the blue line. We will show these functions in green. Our initial guess, V0, corresponds to the horizontal axis. We see that the next iteration gives us a positive intercept and a positive slope. With each successive iteration, the intercept increases and the curvature straightens out. We conclude this video with an animation of value function convergence for our optimal growth model example. We consider the typical case where it is not possible to solve for the value function directly. Instead, one must find the value function numerically using the Bellman operator contraction mapping. For convenience, we restate the Bellman equation for our optimal growth model example here. Recall that V of A is your maximum lifetime utility if your initial resource endowment is A, and that the Bellman equation says that we achieve maximum lifetime utility by choosing current consumption to maximize the sum of current utility and discounted maximum lifetime utility next period. Also recall that maximum lifetime utility next period depends on the amount of resource with which you start next period, which in turn is given by f of k equals f of a minus c. Again, we define the Bellman operator T. To get an upper bound on the argument of the value function, the resource, that is the resource A, it is sufficient to have enough concavity in the production function so that production cannot keep up with depreciation, and f of k is less than k for k above a certain k bar. In this case, if the current resource A is higher than k, even without consuming anything, the next period's resource will be lower. This property allows us to focus on a bounded set of resources, 0 A bar. It can then be shown that the Bellman operator for our optimal growth problem is a contraction mapping with modulus beta on the space of continuous functions on 0 A bar. As before, we apply the Bellman operator iteratively. The first iteration applies the operator to an initial choice, V0. Again, making the standard choice V0 equals 0 yields V1 that simply equals the utility function evaluated at A. The second iteration applies the operator to V1 and so on. To show the results of this iterative process numerically, we need to choose functional forms for U of C and F of K and values for the parameters. Let the utility function U of C have this constant elasticity form. Let the production function have constant elasticity production plus linear depreciation. We use these parameter values. We can solve for K bar using this equation. We then choose A bar equals 120, which is approximately 2 times K bar. We continue to use the discount factor beta equals 0.95. Again, starting from the horizontal axis, we see that the next iteration gives us a positive intercept and a positive slope. The curvature never just goes away, however, because of the concavity of the utility function. Though V0 equals 0 is the natural starting point, theory tells us that the contraction mapping will take us to the unique fixed point, the value function, regardless of where we start. We conclude this video with a demonstration. We start from a sine curve that sits completely above the value function. We see that the first iteration begins to flatten out the fluctuations of the sine curve and reduce the intercept. Each successive iteration continues to flatten the fluctuations and reduce the intercept until we finally arrive at the monotonically increasing shape of the value function. In our examples, we have carefully justified upper bounds for the state variables so that the assumptions that guarantee the existence of a solution for the value function are satisfied. In many optimization problems, however, neither the objective function nor the state variables are bounded from above. It is common practice to pick arbitrary upper bounds and then proceed numerically exactly as we have in our examples. For a mathematically rigorous approach, see these articles. The links to these articles link to the paper by Rauch and Toda in the YouTube description of this video.